Welcome, this is Coach Dorf. Today we're going to continue our discussions about derivatives, and in particular, we're going to talk about derivatives of log functions. Now, in the past several lessons, we've talked about derivatives of polynomials using the power rule, the quotient rule, the product rule, and the chain rule. We've also talked about derivatives of the exponential function f of x equals e to the x, and we talked about derivatives of trig functions, but we haven't talked yet about derivatives of log functions. So that's what we're going to focus on today. So we'll just start off here. What is the derivative of the natural log of g of x? That's going to be g prime of x over g of x. Another way of thinking about this is if I have the derivative of the natural log of a box. So what I mean by a box is I could put any function inside that box, then that derivative is going to be the derivative of the box over box. Let's give an example of this. So let's differentiate the following log function, the natural log of x squared plus 3x minus 1. All right, so what's the derivative of that? Well, by this rule, it's going to be y prime is going to equal the derivative of what's inside that parentheses over what's inside that parentheses. So when I do that now, so I've got x squared plus 3x minus 1. I want to take the derivative of that, put that on the top, and then put the x squared plus 3x minus 1 in the denominator. If I take the derivative of what's on the top, I can use the power rule, and I get 2x plus 3, and in the denominator, it just stays the same. And that's my answer. Pretty straightforward in an example like this. Let's do another example. So here we're going to differentiate. This time we're going to involve a trig function. So we're going to differentiate the natural log cosine of x. I'll call this y here. I should have called this y up here too. So solution here is going to be, y prime is going to be, so I'm going to take what's inside the parentheses, put that on the top, and take the derivative of that over what's inside the parentheses. So derivative of cosine is negative sine, and that's all over cosine. And then I can simplify this. Sine over cosine is tangent, so I end up with negative tangent. All right, let's talk about what if I have the case of just the derivative of the natural log of x. Well, what would that be? Well, by this rule that we have here, the derivative would be, derivative of natural log of x would be x, the derivative of x over x, and the derivative of x is 1, so we get 1 over x. So we have this rule 2, that's just is a special case of what we did before, that the derivative of the natural log of x is 1 over x. And this makes sense if we look at the graphs of the function. Remember that the graph of the derivative, or sorry, the graph of the natural log of x looks like this, y equals natural log of x. And now if I take the graph of its derivative, let's say y prime, without even knowing what the answer is, what do we do? Well, we're going to take, since we have a graph, we're going to take the slope of the tangent lines. So I take a point on the curve, there's my tangent line, there's another point on the curve, another point on the curve, another point on the curve. What happens? Well, I start off here, my slope is a positive, in fact, for all these points on here, the slope is a positive number. When I'm farther to the left, closer to the y-axis here, that slope is a really high positive number. And as I go farther to the right, as x gets farther to the right, my slope is still positive, but it becomes smaller and smaller, and eventually it gets close to 0. So that means when I'm looking at the graph of the derivative, when I'm close to the x to the y-axis, so x is close to 0, but a positive number, I have a very high positive number, and then it's decreasing, and it's getting closer and closer to 0. So that's what the graph of the derivative would look like. And what is that graph? That is 1 over x. So the graph of the derivative is 1 over x. And that matches this definition, or what I have in this box right here, right? That matches that. How do we prove this, or how could we get this? So how do we get this result that we just stated at the very beginning? Well, we're going to start off by letting y equals natural log of x. And we're going to use the idea of inverses. So the inverse for this of natural log would be e. And we could remember then that x equals e to the y in this case. Or if you don't remember that, what you could just do is take e and put it to the power of both the sides of here, this equal part. So I get e to the y equals e to the natural log of x. And when I have e to the natural log, that just becomes, those disappear and I just get x. So y equaling natural log of x is the same thing as saying x equals e to the y. All right, and so now we're going to take this, what we just have here, and we're going to use implicit differentiation that we talked about last time. Differentiation, did I spell that right? I hope I did. Don't always remember how to spell these things when I'm working on differentiation. I think that's right. All right, so now what do we do when we do implicit differentiation? We're going to take d dx of both sides that's in the circle red part here, right? We're going to take d dx of everything here. So we have d dx of x on the left side, and we have d dx of e to the y. All right, when we talked about implicit differentiation, when we do d dx of x, that's just going to be 1. And now when we, on the right side, we take d dx of e to the y. So the derivative of e to the y is e to the y. But because my variable there is a y, which is dependent upon x, I get a dy dx. So then if I need to solve for dy dx. So I bring the e to the y over to the other side. So I get 1 over y equals dy dx. And what is e to the y? Well, right here, we go back up to that red box there and we see that e to the y is x. So when we substitute that in there, we get 1 over x equals dy dx, which is then what we have here. That's what we said in this box here. Because dy dx is the derivative. This is the same thing as the derivative of the natural log of x. So we get that the derivative of the natural log of x equals 1 over x. And how do we get the rule that we had earlier that we stated at the very beginning? d dx of the natural log of g of x equals g prime of x over g of x. How do we get that? Well, we just use what we proved here along with the chain rule. So use the chain rule with this that we just proved here to get this result here. And one of the things that's really nice about this too is it's very satisfying that we have a gap before today. We had a gap in some of our derivatives in our patterns. So let me show you a pattern here. If I had 1/3 x cubed and I took its derivative, that would be x squared. And if I did 1/2 x squared and took its derivative, I get x to the first. And if I did x to the first and took its derivative, I'd get 1, which is the same thing as x to the 0. And if I did negative x to the negative 1, and I took its derivative, I'd get x to the negative 2. And if I did negative 1/2, x to the negative 2 derivative, I would get x to the negative 3. And there's a nice pattern here on the right side, except we're missing something. We're missing x to the negative 1, which is 1 over x. Before today, we didn't have that. What would go in here? Well, what goes in there is now the natural log of x equals the negative 1 over x. So from today, we get to fill in that missing spot. And that's kind of satisfying to have that pattern keep working like it does there. Let's do a little bit more complicated example of this natural log. So we're going to do the following example. We're going to differentiate f of x equaling the natural log of the square root of 1 minus x squared. So what we've done before works fine here. So the derivative is going to equal what's on top. Oh, wait a minute. Before I do that, let's just go ahead and rewrite this because it might be, I think it's be easier. So f of x is the natural log of this, but let's write that as the natural log of 1 minus x squared to the 1/2 power. And you'll see why I want to do that as we go through this discussion. So it's okay if you don't see it now why that's useful, but we'll go ahead and we'll do this. So now take the derivative of a natural log. I take what's in the parentheses after it. So I've got 1 minus x squared to the 1/2 power. Remember, you still have to have that 1/2 power there. And I'm taking the derivative of that. So let me just call that d dx, all right, over what I have after the natural log. So same thing, it's g prime over g. So it's the derivative of 1 minus x squared all to the 1/2 power over 1 minus x squared to the 1/2 power. All right, and how do I take that derivative on the top? Well, now I need to use the chain rule. So the chain rule says I'm going to have basically what side inside the parentheses there to the 1/2 power. So by the chain rule, that derivative is going to, I'm going to bring that exponent out front, keep the parentheses, reduce the exponent by 1, and then I have to take the derivative of what's inside the parentheses. That's the chain rule. So let me just highlight that. This is from the chain rule. So this kind of is reviewing what we've talked about before, but that's good to review that. And then I have keep the denominator the same because I'm not taking any derivative there. All right. And so then I'm going to get, let's fill some of this in. What's inside the parentheses here? It was the 1 minus x squared. So I'm writing that in red so you can see that. And so when I do that, I'm going to now write it in black here. Now I take this derivative here, I'm circling in blue, and that derivative is going to be minus 2x. That's all over the denominator. Oops. And now I've got this here with this negative exponent, negative 1/2 exponent. Let's put that in the denominator. So I'm going to still have that 1/2, and I'm going to still have a negative 2x in the numerator. But now I'm going to take that, what's that in that green, and move it to the denominator. And I can do that if I change the exponent to a positive 1/2. And then I also have that positive 1, that positive 1/2 from here. So this is this one, and this gives me this one here. Then when I combine those together, in the denominator, I've got 1 minus x squared to the 1/2 times 1 minus x squared to the 1/2. So that just gives me 1 minus x squared to the 1 power, because I just add the exponents. And in the numerator, I can cancel out the 2's so that I end up with a negative x in the top. And so then I can just write that as negative x over 1 minus x squared. And that's my answer. Now, there's another way to do this. And let me just show you this. And this happens often in math. There's more than one way to get the correct answer. All right. One thing that's nice about math is when you do problems like this, there is a correct answer, but there's more than one way to do it. So let me talk about another way to do this. Remember, what we're trying to do is we have this function f of x equals the natural log of the square root of 1 minus x squared, which we wrote as the natural log of parentheses 1 minus x squared to the 1/2 power. Recall here that when I have the log of something to an exponent, so I have the log of a base part to an exponent, one of the rules of the logs is I can bring that exponent out front. So this is the same thing as equaling 1/2 natural log of 1 minus x squared. All right, that rule that we talked about, it's a long time ago we talked about it, but if you have the log base a of x to the r, that equals r, you bring this out front, r times log base a of x. That's the rule that we're applying here. So let's look at this. Then let's look at the derivative of this. So we're gonna, let me rewrite the problem again here. So we have, this is going to be equal to this. And now let's take derivative of this. So the derivative is going to equal 1/2. That 1/2 stays up front. And then I'm going to do the derivative of the natural log of 1 minus x squared. And that is going to equal, by the rule that we talked about here, that if you take the derivative of the natural log of g of x, it's g prime of x over g of x. So it's going to equal the derivative of that parentheses over that parentheses. So that is what? What's the derivative of the parentheses? And in the numerator, we have minus 2x. And in the denominator, we have this. And then those 2's cancel out, and we end up with negative x over 1 minus x squared. And notice that that answer is the same as this answer here. We got the same answer. You can do either way. Which way is quicker? Well, this second way is kind of quicker, I would say, but you don't have to do it this way. You could do it the first way, which would probably be what most people would think of doing it in the first time you approach this problem. All right, let's see. So one thing that, let's recap some of the things that we've talked about here. So this is going to be like a recap. All right, if I have the function y equals x to the 4th, then we know that its derivative is, by the power rule, 4x cubed. That comes from the power rule. And we also saw that if we switch these around now, instead of having, in that first one, my variable is in the base and my exponent's a constant. We can switch that around to put now the constant in the base and the exponent is the variable. And we learned a few days ago when we were talking about the chain rule that the derivative of that is 4 to the x times the natural log of 4. What if we have now the case where we have the variable both in the base and in the exponent? Then what is the derivative here? We haven't talked about that yet, but now we're in a situation where we can talk about this. And this is going to be, to do this, to solve 3, we use a thing that's called logarithmic, hope I can spell this right, differentiation. So this is a technique that we'll use to solve this. And for logarithmic differentiation, there are some steps. And let me just write those steps out. We're going to have a summary of steps here. Oh, that's not. Let me rewrite that. Summary of steps. So the first step is you take ln of both sides. And let me just remember, in this case, what we're looking at is something like this blue circled one here, where the variable both in the base and in the exponent. So first thing I do is I take ln of both sides and I differentiate implicitly, and then I solve for dy dx. And then the fourth thing is I make sure the answer has no y terms. And maybe I put up here in this first step, I take the natural log of both sides and I use the fact that we talked about earlier, that the natural log of x to the r equals r natural log of x. We're going to use that fact there. So let's do an example of this approach here. So we're going to differentiate the following function. It's going to be equals x to the sine x. The first thing we notice here on this problem, my base is an x and my exponent has an x in it too. So I can't do the power rule. If this were x to the 4th, I could do the power rule. And if it was 4 to the x, I could do the chain rule and get that the derivative is 4 to the x natural log of 4. But here, I can't do either of those because I have an x in the base, that blue part, and I have an x in the exponent because I have sine x there in the green. So we use rhythmic differentiation here, which I'm going to abbreviate there. So I start with y equals x sine x. So step 1, all right, is I take the natural log of both sides. So natural log of y, natural log of x sine x. So that's step 1 there. And now, why is this a good thing to do? Because I want to get rid of that x variable in the exponent. I've got that sine x in this case there. I want to get that out of the exponent. Well, I can now use this log rule that I had circled in red there to take this natural log, this sine x that's in the derivative, and bring it out front so that I get sine x times natural log of x. So now I have that. Now that's really great because I've gotten rid of the x in the exponent. So I can use step 2, which is to use implicit differentiation here. That's step 2 here. So I'm going to take d dx of the natural log of y, and I'm going to take d dx of sine x times natural log of x. All right, when I do that on the left side, then the derivative of natural log of y is 1 over y, because that's what we talked about, right? The derivative of the natural log of x is 1 over x. The derivative of natural log of y is 1 over y. If you wanted to think about it, you could write this as y prime over y, but we get that because on the left side, when we do d dx of natural log of y, because y is dependent upon the x variable, we get a dy dx. So that's the y prime part there. All right. And on the right side, I get what? Well, I've got to use the product rule here. To use product rule because it's the multiplication of 2 functions. So when I do that, I get the first times the derivative of the second plus the second times the derivative of the first. And notice here, whenever these steps, what I've circled in red, the fact that we're going to take that sine x, the part that's circled in red, bring it out front. That will happen every time when we do logarithmic differentiation. Well, we won't have sine x there, but we could have some other function of x. It could be x to the x power, or it could be x to the 1 over x power. I'm always going to have something there. So the red, I'm always going to bring that out front. And then when I do the implicit differentiation on the right side, I'm always going to use the product rule because I'll always have the product of two functions there. Now let's simplify this a little bit. We've got 1 over x times dy dx equals sine x. And now I take the derivative of the natural log of x, which is 1 over x. And then I got plus natural log of x times derivative of sine x, which is cosine x. All right, good. Now I do step 3. Step 3 is I solve here in green, here solve for dy dx. So I'm going to solve for dy dx here. So I got dy dx. To solve for that, I'm going to multiply both sides by y. I'm going to put a big parentheses here because everything is going to be multiplied by y. And then I do the last step, which says make sure everything, the answer has no y's in it. Well, we have a y here. So to do that here, I've got to rewrite that y. What does y equal? So no equals, if we go back to the very beginning here, equals x sine x. That came from up here. So then we're going to replace that in here to get dy dx equals, so here we had y, but now we're going to put in x sine x, and then we're going to put in, just copy what we had before to get this. And that's my answer. All right. So you'll see you use this logarithmic differentiation whenever you have the variable in the base and in the exponent. So some examples, if you had y equals x to the x, you would be using it. If you had y equals x to the 1 over x, you'd use it. If you had equals x to the cosine x, you'd use it. You'd also use it if you had equals cosine x all to the x power, or you can have it y equals square root of x to the x power. All those cases you'd use logarithmic differentiation in solving this. All right. Another topic for today is what are the derivatives of inverse trig functions? We haven't talked about that yet. So we're going to quickly discuss that here. So there's a bunch of formulas for this. So we're going to have, what are my inverse trig functions? Well, I've got arctangent, or also written as tangent with the -1 up there. Derivative of that is going to be 1 over 1 plus x squared. That's 1, 2, and if I have d dx of the inverse sine or arc sine, that's going to be 1 over the square root of 1 minus x squared. Then we have the derivative of arc cosine or inverse sine, like inverse cosine, and that's going to be -1 over 1 minus x squared. So it's the same as the inverse sine, but it's got a negative in front of it. And then we've got our other functions. We've got inverse secant, which is going to be 1 over x times the square root of x squared minus 1. And we've got derivative of inverse cosecant is -1 over x squared minus 1. And last, we have the derivative inverse cotangent or arc cotangent, and that's going to be -1 over 1 plus x squared. Notice, just like when we had our derivatives of the trig functions, anything that, if I'm taking the derivative of something that's a it's going to have a negative. So we have cosine, it has a negative derivative. Cosecant has a negative. Cotangent has a negative. Also, if you subtract the cos, there you get the same formulas without the negatives. So sine and cosine both give you the same thing. It's just that the one has a negative. If I do secant and cosecant, so they're cos of each other, they have the same formula, the derivative, except the one has a negative in front of it. And then likewise for the tangent and the cotangent, they're related. They're just one's of the other. They have the same formula, but one has a negative in front of it. Now, my experience is, which ones of these should you know? Well, that method I just showed you, where you associate the regular one with the and that they have the same formula, except the one has a negative, helps you memorize all these. Usually, though, when I've seen these on homework and on tests, the first three, 1, 2, and 3, are the ones that are that you see on most of the tests there. Let's give an example of this, because it's not just a straight plugging in of here. So we want to differentiate capital F of the arc sine or inverse sine of 2x minus 1. Now recall what's the formula here for inverse sine, for the derivative of it. The derivative of inverse sine of x is 1 over the square root of 1 minus x squared. Now this one is different, this example, because we have this. So we have to use the chain rule, and you're going to use the chain rule a lot. It's just going to keep coming back. So what we get here basically is, when I do this derivative here, it's going to be the derivative of the box over 1 minus box squared, the square root of 1 minus box squared. So let me rewrite that. So really, when I'm looking at this, what this is saying is, if I have the inverse sine of box, it's going to be the derivative of box over the square root of 1 minus box squared. So in this particular case, we have, so here we have the derivative of the inverse sine of our box, and what's inside our box? It is 2x minus 1. That's what's inside of it. So what I'm going to get is the derivative of that box over the square root of 1 minus box squared. And so I'm going to just put inside that box 2x minus 1 and 2x minus 1. And so when I do that now, and I compute this, I get on the top, the derivative of 2x minus 1 is 2. And then in the bottom, I get 1 minus 2x minus 1 quantity squared. All right. And that is my answer for this one. Let me just do one last example here. And this example is following: if f of x equals arctan of x squared, find the derivative evaluated at 2. So we need to remember what's the derivative of arctan, or inverse tangent. So the inverse tangent of x equals 1 over 1 plus x squared. That was what we had earlier. If I just remember that, going up here to number 1, that's what number 1 says. So that's where we get that from. And because I'm going to be using the chain rule, because notice I don't have just an x there, I've got the x squared. So by the chain rule, I'm going to have that the inverse tangent of box is going to equal the derivative of box over 1 plus box squared. That's the equivalent of using the chain rule. So for our f of x equaling arctan of x squared, we're going to have the derivative of the box is going to equal d dx of the box over 1 plus box squared. And now what's inside the box? Inside the box is x squared there. And so then we can simplify that. The derivative of x squared is 2x. So that's what this is, over 1 plus, and now I have x squared, which is the same thing as x to the 4th. We're not done, because it said find the derivative at 2. So now we're going to have to plug in 2 there for x, and we get 4 over 17. Let me end with one last thing. Where do these formulas come from? Do these inverse derivatives of inverse trig formulas come from? Well, it's going to be the same thing as how we got the derivative of the natural log of x. So we're going to do an example here. We just showed that at the derivative of the inverse tangent, or we just used the derivative of the inverse tangent is 1 over 1 plus x squared. So why is that? Well, that's funny to say why is that, because now I'm going to say y is, okay, because y is inverse tangent of x. So maybe I should have said, instead of y there, I should have said how come, so we don't get our y's mixed up. So we got equals inverse tangent of x. That's equivalent. Now, if we want to get rid of the inverse tangent, because we don't know what its derivative is, we can do that by taking the tangent of both sides, or thinking of it this way: y equals the inverse tangent of x is the same thing as saying tan y equals x. Now, we can take the derivative of tan y by using implicit differentiation. So by implicit differentiation, we do d dx of tan y equals d dx of x. So then the derivative of tangent is secant squared y. And because y is dependent upon x, we get a dy dx. And think of that as implicit differentiation. You can think of it as chain rule. And then on the right side, we have d dx of x, and that's just 1. So we want to solve for dy dx. So dy dx, I'm going to bring the secant squared of y over to the other side, and I get this. Now, we'd be done, except that we want to have x's here. We don't want the y's here. We need x here on y. How do we get rid of that? Well, the only thing we have is that we know that x equals tan y. So is there a way to rewrite secant y in terms of tangent? Because then we can put the x's in there. And we can. We use the trig identity that 1 plus tan x, tan squared of y equals secant squared y. And just as a review, where does that come from? Remember, so we know that the most famous or most important trig identity is cosine squared of y plus sine squared of y equals 1. So now divide both sides by cosine squared y to this. So we get cosine squared y over cosine squared y plus sine squared y over cosine squared y equals 1 over cosine squared y. And what does that simplify to? Well, that gives me, I get 1 when I have cosine squared over cosine squared, and then sine squared y over cosine squared is tangent squared, and 1 over cosine squared is secant squared. So that's where we get this identity from, just starting from the original one. So we're going to use that idea. Remember where we were at, we had dy dx equals 1 over secant squared y. We get that from just right up there. And now we're going to use the fact that secant squared is equal to 1 over tangent squared. So I get that's the same as 1 over tangent squared y. But we recall that from the very beginning up here, we had tan y equals x, tan y equals x. So when I substitute that in, we get dx equals 1 over 1 plus x squared. And that's the formula for the derivative of the inverse tangent. That's how you can get all these derivatives of inverse tangent functions. All right, hope that helps you. Have a great day.